First of all, I'm very happy to be here, and it's my pleasure and honor. And I should just start by saying that you guys are in excellent hands to have somebody like Paul Messina organize this whole conference and boot camp, so to speak. When I was I'm not that old, but when I was your age, graduated and started as an assistant professor, I had I was very fortunate to uh, be able to work with Paul and collaborate with him, and that had a tremendous impact on my personal career. And not only did I learn about technology and so on, but I also learned about how to build teams, how to think big picture, how to bring people together, and so on. So I'm very happy to be here, and I'm very grateful to Paul for inviting me for this talk. This is it's an experiment. This talk is an experiment, and I will talk about a few things. I'm sure you heard about big data, extreme scale, exascale, et cetera, right? So I've been thinking about this topic for a bit. Doing things like big data before it was called big data, as Paul mentioned. And I'll just try to, of course, put together or talk about extreme scale computing and big data and what are the, how they go together, where are the challenges, and so on. But I'm also going to try to explain what big data analytics or big data computing means. And given the amount of time we have, I'm not going to talk about many of the user-centric aspects of when you use Google or Facebook, the user experience, but that's an important part of big data. So just to point out that there are the material that you will see comes from many people. University of Minnesota and Northwestern and NC State and various collaborators. So you'll see some of those things. But I try to keep it at high level. So one of the theme you say time to compute to actionable insights, right? What does that mean? So a lot of us who do computational science or use big systems, we are always focused on how long does it take to do my job, not job as a professor, but my job on the computer, right? And that's what I call transactional thinking, okay? So what we have to sort of strive for, and if we start to think about how long does it really take to get insights, particularly those that are actionable. Now, actionable insights do not necessarily apply in all science domains, right? Because actionable insights in climate could mean policymakers have to do something, right? On the other hand, in medicine, it could mean acceleration of drug discovery and so on, right? Or in the business world, which product to recommend to a customer, right? So if we start to think about what it means to get there, then we can start to go beyond the transactional thinking, and that's the sort of theme that I have put together. So the first thing I would like to and please feel free to ask me any questions. And I know it's being recorded, so I have to be careful. So first thing that we want to understand is when we talk about big data, what does it mean? Okay. So I've divided, I was talking earlier to, I don't want to embarrass her, but one of my students is also fortunate to be here. And I'm saying, okay, I always have, every talk I have a one triangle diagram, okay? That means, you have three legs of a stool to keep things stable. So in this particular case, I say, okay, big data is sort of in science, right? I mean, if you look at those Nature, Science, etc., those magazines, they have whole issues on that, right? So everybody's talking about it. In science, where is it coming from? Whether you have high throughput devices, you have satellites, you have sensors, etc., but also supercomputers. I believe a supercomputer is like an instrument, right? If you close your eyes and say, hey, all the data that I see which is coming from LHC, instead of that, if I told you, hey, it came from a supercomputer, you wouldn't know the difference, right? So the point is that supercomputer is a generator of data, and then what you want to do is go to knowledge discovery. And of course, in the business world, I'm sure, how many of you use Facebook? Who doesn't use Facebook? Okay. Twitter. Okay, so all of you are in my database. So, and then one more point I'd like to make. So big data is not, is a business thing or a social thing or a science thing. It is the way you think about solving the problem using data. So again, when I talk to many people and when I look at various things, people will use the word data intensive computing to interchange with data. In my opinion, data intensive computing is in the eye of the beholder. Okay? So if I'm a cache memory designer, data intensive computing is a characteristic of an application or a code where I get a lot of cache misses, a lot of streaming of data. Right? It doesn't mean that it's terabytes of data as long as the access patterns are different. So that's data intensive computing essentially means what, if you're solving a particular engineering problem or any other problem, what is the impact of data movement and processing within that context, right? For a I/O system, it may mean something else. Doesn't mean it's huge amount of data. You have latency and you have response time requirements. On the other hand, when I think about big data, I think about data-driven computing. Okay, so what is data-driven computing? Data-driven computing is that the computing is initiated by the data. So you divide the data generation, and then, so if you take Google, right, or you take Facebook, it's the world which is creating the data, right? And if you didn't have the data, Google's search engine won't mean much, or Amazon's recommendation engine won't mean much, because there's no data or behavior to process. Similarly, if you didn't have sensors and other things, observing climate and so on, you won't have any processing to do, right? So data-driven processing, where the data sort of starts the computing, that's what I think is part of big data computing, right? Now, data can come from simulations or data can come from somewhere else. It doesn't mean that things are not important in one domain or other, but that's where you start. And within that, there are two types of, one is top-down, and I'll talk a little more, and then one other is bottom-up. The thing that I will not talk about is the user model, but I just want to make one point. If you sit back and think about science versus business, just two domains, you have to think about who is the end user of the data, right? In science, let's say I'm doing combustion simulations and I have ensembles of data, or I'm doing climate modeling and so on. It's the scientists, people who understand the domain well, who are the end user of the data. So you don't have to take that big step of presenting the results in a way which are very actionable for the end user. On the other hand, when Google does big data, their end user is not a scientist or a domain expert. It's a mom or pop or a cousin or a son who's looking at this. Both are big data, but that big step that is required, and that's where a lot of the differences also come into how you can process. And the correlation of data is also important, science versus business. So what I'm going to do now is I'm going to take one specific problem that I've personally been working on. You probably see it in the press. And I'm going to try to use that to connect, describe what big data in science domain means, what extreme scale means, what does it and how is it connected, right? And then I'll give a couple of other examples if the time permits. I'm sure a lot of you read in the press and see, and many of you may be involved in climate simulations and so on. CO2 levels hit new peak at key observatories. That's a news item. So what are we talking about here? We are talking about an observation or potentially result of a simulation, right? And so you do different scenarios. Okay, so what this shows is, okay, this here in time, if we think about how much pollution, carbon, other things the world is generating, then if you have a scenario where you make an assumption that low amount of emission will exist, then this is where the carbon, some whatever measure that be, if it's a higher emission, it'll be there compared to what you see historically. So that's a observation, that's simulations, predict, et cetera, right? So high performance computing comes into play where there's a lot of math and so on. So what is this? So this is a problem in climate understanding, right? So this is based on a physics approach, right? You're building all these models and hypotheses and equations, and then you're using the domain and you're creating initial conditions and you're doing all those things, and then you are simulating to predict something in the future, right? So here is some fancy chart from NCAR about one of these things, one of the parameters. But the most important thing to remember is that it's based on mathematical model, right? So what the data can do here is change the initial condition, right? So if you did start 5 years ago, you could look at the latest initial conditions and use that to do your model. Now today you can do something different. But it's the future. Future is completely based on prediction, is completely based on mathematical models, right? So you said this is great. Is it? It's science-driven, physics-based. We know, and this is fantastic. IPCC guys, those codes, they got the Nobel Prize, et cetera, et cetera. Okay. So what is this? How do I go next? Okay. Did we go next? Okay. So, okay, so these are also called, and there's nothing new I'm talking about here. I'm just trying to put it in a particular way of thinking about this. Okay. So what this shows is that physics-based model, you can globally average surface air temperature, okay? And you see a particular pattern, right? Now, depending on what your politics is and what your science is and what your expertise is, you may agree, you may not agree, so you have ensembles. So there will be a bunch of these models, collection of these models, and you look at averages. Okay, so what is the point? So if I look at ensemble averages, so if you are interested, you go, I look at IPCC codes, there are a bunch of different types of codes, they take and average it, et cetera, et cetera. So this is what you will see, and then the corresponding band which gives the uncertainty and so on. Okay. So this is with the observed greenhouse gas concentration. Okay. You're thinking, okay, where is this guy going? Where is the big data here? Okay. So now, okay, so this is all controversial as well, right? So now if they did the same simulation and removed, did with the pre-industrial greenhouse levels, then in fact it's predicted to actually cool down. The planet is predicted to cool down. Okay. So this is great information, right? So what this says is, okay, we are going to have global warming, and now what do we do? Is it an actionable insight? Is it an actionable insight? Yes? No? I'm going to ask, can you take an action based on this? What action could you take based on this information? Sorry? So
you need to make the upper cap meet the lower one, so you reduce the...
I know what the goal is. What is the action? All right? You see? You see? It's not so easy. It's not so easy to think about, okay, I've seen this is cool, this is great, what do I do? Right? Actionable insight means, hey, let's do this, make this decision, invest this, go to electric cars or whatever, right? It's not an easy thing. But that's a, that's a side discussion. But there is another major point, right? If I told you, so you live in Minnesota, right? Would you be happy with this result? Let's say you're northern tip of Minnesota. You say, oh. I say, yeah, I'll be very happy with 2 degrees more average time, right? So now it's also very local, right? It's not so easy to get your hands around this. what we call the side effects and the unintended consequences and so on and so forth. But in Florida, maybe your beaches will go away and so on. So that's the whole point of what we are looking at with the temperature data, right? Just it's average of one parameter. Right? And I'm not, I'm not a climate scientist, so this is my external observation and learning. So now I could take different emission scenarios, and I can go and I can do whatever observation initial condition, and I can do a 100-year simulation, right? Supercomputer, exascale. If I have exascale, I can reduce the grid from 10 by 10 kilometers to 1 by 1 kilometer and get better results, more accuracy, but I'll still know the average temperature. I'll say instead of 1.5 degrees, it's going to increase by 1.6 degrees, better accuracy, but only the average of global temperature, still not actionable, right? Physics-based models are essential but not sufficient if you want to get to actionable insights. Not are necessary, are very important. You have Miami Hurricane Center churning away on supercomputer. The sad truth of climate science, so this is again one example. It doesn't mean that it applies everywhere, but it does apply to many other places. In predicting using mathematical models and simulation, the relative reliable prediction for things like temperature, pressure, this is pretty good, right? You can validate, you can go back and you have observational data. But these have very high uncertainty when you think of things like hurricanes and extremes. Extremes are what? Droughts or floods or any extreme event, right? And so on. So these are good. Physics-based simulation models are not so good, right? Now, if I asked you, if you had better information, if you could predict the hurricanes better, is that let's say instead of 2 days before, you could predict the hurricane very accurately 5 days before it strikes. So that's how you have to think about it. So now you say, okay, how do I solve those problems? Because it's part of the climate change. Okay, so of course this is from Nature Climate. They are also talking about big data, big science, and so on, and its societal importance. And so, okay, so now let's talk about data within climate. Okay, so it's become data poor to data rich, right? You have sensors all over the world. You have all the satellites, you have all the balloons, you have the NASA stuff, you have DOE, you have different countries, planes flying through things, and so on. So there is a huge amount of data. Okay? Now, data is not very structured in every grid point that you see nicely in a simulation, right? So then there is a massive analysis which is called reanalysis required to to get the points that may be missing and so on. And of course, there is massive amounts of model simulation data. And again, there are two important aspects, right? Models are, so when you observe something, let's say you have a some sensor there, and you say in your AC in your room say 72 degrees, right? There is no dispute. You say, okay, that's the sensor, it's pretty accurate. Different models have different math, different people, different politics, there is a lot of that, right? So there are a bunch of data sets, right? They are not shared around. They are not put together. But there is some knowledge that may be missing. Okay, so very quickly, one can bring in, and this is pretty recent, you might be surprised, bring in data-driven approach, which take observational data, which take simulation data, and then start to look at extreme events and other things. We may think that we are very advanced in that, but that's not true. Okay. So in fact, when Hurricane Sandy struck the East Coast, its prediction of its path was more accurate than general, and one of the main reasons for that was that the rate at which data was collected was 4 times the normal rate by US government repurposing its satellites and others to collect that data. right? So it was the increase in the data that allowed better prediction. Okay. So you can do data-driven approaches, and you can talk about, you can start to look at those problems by understanding and combining things together, where it's not only science data but others. What data-driven approach also allows you to do is to bring in the domain knowledge. I mean, a local person, a farmer in Africa knows a lot about how things change than a mathematical model. How do you bring in the domain knowledge? That's also data-driven computing that allows you to do. Of course, there are still problems that are very hard to even do, like fires and other things. Okay, so given that we want to do data-driven, big data analytics, and we want to get actionable insights, so let's assume that we have a way to getting all this data and so on, right? So the question is, how do you get a handle on what type of problems, what are the methods to solve these problems? Okay, so so in order to get a handle, right, different people, you go and talk to somebody and you say, oh, I have a Excel spreadsheet and my customer data or this data is on a spreadsheet and I do regression on that data, right? They'll say something like that. What does that mean, right? What is the end goal? So what I like is to see what are the different ways of dividing the data-driven computing, the data mining approach, data analytics approach, and then how to define your problem. That's the most important thing. And then what your end goal is. So I'm sure you're familiar with this, but at the top of this sort of, I call it, it's really not a poem, but I just call it a poem. So the unknown, and I'm sure a lot of you have seen this before. So as we know, there are known knowns. Any known knowns? Do we know how the world was created? It depends on what your politics is, right? I'm just kidding. Okay. So, but of course, so there is a hypothesis that the world there was a big bang, etc., and then we use science and big data analytics to validate that hypothesis. So we assume that you have a known, the sun rises from the east, etc. That's a known, and then you validate the hypothesis, right? You make a hypothesis, use observational data, and invalidate, right? So we used to think, okay, sun goes around the earth, right? Long time ago. It's a data-driven discovery problem, right? So somebody observed and said, oh, no, it's the other way. But politics was very difficult at that time, right? Okay, so as an example, what you're doing is you're saying, okay, I have some conventional wisdom. Can I validate that, right? So now you can define your problem in that context. So high humidity results in outbreak of meningitis in certain, Horn of Africa. It's a known thing. So now can you validate by observational data, etc.? And then if you can do that using historical data, and then you know that this is going to happen, then you can take actions. You can go to Bill Gates and say, hey, $20 million for vaccines because this is going to happen. That's actionable insight, but it is driven by data. Okay, so you're validating hypothesis, these are just an example for that. Okay, so that's one way of formulating your, okay. Then the second thing is we also know there are known unknowns, okay. So there are things that we know we don't know. This is like, in the Cold War days, you just probably see these people sitting in CIA and the KGB, and one is saying, do they know what we know? So, yeah. But do they know we know what they know? And then you just go on, so right? So it's like a game. So the point is that we know there are some things we do not know, but we know what to ask for, right? So it's a second thing. So how in the data-driven approach, what is the problem formulation? So this is called top-down discovery. We know the question to ask. We can formulate a question, right? Will this hurricane strike the Atlantic coast, right? That's the question for the US government. Question for the governor of North Carolina is different. Will this strike North Carolina, right? Question for Charlotte, I don't know, is Charlotte on the coast or I don't know, okay. So, pretend it's on the coast. So then it's okay. So there are different types of questions, right? So formulation is, but you know what question to ask, right? Or what is the likelihood of this patient to develop cancer? You have historical data, what is the, et cetera, et cetera. So you have to now start looking and learning from the data and say, okay, I can say with certain certainty, this is what is going to happen. But you know the question to ask, very well defined, and now you can have other things. Okay, I want confidence of 95%, right? It means I can only be wrong 5% of the time. Now, if you think about this, it's a very important aspect in defining the problems and so on. Doesn't matter where the data is coming from. Let's say you go to, not you, but let's say person A, lady A, goes to a doctor's office, and doctor says, oh, I have this little lump. What is the prognosis or diagnosis, whatever, right? And doctor says, I don't know. Will you have? I predict that you will develop breast cancer, or I predict that you will not develop breast cancer. Which side should doctor go wrong on? What is the cost? Say, so the breast cancer is developed, but doctor said, no, you are not going to have. Is that a good thing? No, right? You would want to know with high probability whether it is. But let's say if the doctor said, you will develop breast cancer and you don't develop. Is that a good thing?
Depends on the action.
Right? Okay, what that will result in potentially additional tests and so on and so forth, additional expense, but you can afford to go wrong in that direction, little more. So it's not a single thing, okay, my question, do I know X? It's a very scientific, that's what you hear, that the world needs 500,000 data scientists, right? So, so that's how you present. And then, of course, the third thing is there are also unknowns. There are things that we don't know, right? You agree? Right? Okay. There are unknown, we have no clue, right? That if there are things that, so what is that, right? That is called bottom-up discovery. Okay, so we don't even know what question to ask, right? So you are looking at some data from galaxy and you're not asking, is there a galaxy here? Is there a galaxy here? Is there a, hey, here is something interesting. You find a signature that you've never seen before. And then you start to ask questions, what is it, and so on. Or you discover that based on the data, you can't model this. Switch C fails when if I look at time series data, when switch A fails followed by switch B failing, right? Number of combinations is in billions and trillions, right? So you cannot have top down, so you have to have bottom up. So those are the three ways of formulating the problems in this. Of course, this is a quote from Donald Rumsfeld when he was asked about what's happening in Iraq. So this was his answer, okay? No, seriously. Now, journalists didn't know that this is originally written by Socrates hundreds of years ago. But anyway, so it's still relevant today. Okay. So let's sort of move on and say, okay, now when you come back to supercomputing world or data generation, we are always thinking about this transaction thing. How fast my program ran, I dump the data, I visualize it, and I go home, right? But we are never, the data-driven big data processing is, there are a bunch of other steps that are very important, right? So can I collect historical data, right? I've done, there are tens of, at least hundreds of people who are doing material simulation, right? That data never gets put together in a way where you can find something interesting. If you look at individual points, you don't see a pattern, right? That's the whole point. So in order to get there in this, you have to sort of start to look at this whole virtuous cycle, knowledge discovery cycle. Right, so you're generating data. Now the challenges would be different from different domains, but the formulation would be similar, right? So, and then data analytics. So I gave you examples, 3 different ways of looking, et cetera, and then you go there. Now that's a big challenge. So here is an example of, I was just talking about the hurricane. These are the steps: data generated, simulation, observation, processing, combining with historical data, transforming into a network problem, right? And then saying, okay, my question to ask is, will the hurricane strike this? Right, so that's the whole point here. Okay, so and this is both computer science challenges, right? So those are contrast-based network mining for. We don't have to understand what that means at this point, but techniques that people in computer science, what is the impact of this improved forecast skill for seasonal hurricane activity? Very actionable, very valuable to society and so on. So that's what data-driven big data computing is all about. There are a bunch of challenges. So if you are a geek and say, okay, what does it mean in statistical term, and so all that. So these are all the things that we don't know how to do today. Okay, and there are many, many more. How to deal with non-IID data and spatio-temporal correlations and so on. These are all open problems, particularly scaling to large data. I'm personally very interested in science, right? I was not joking about Facebook and so on. The way I started thinking about this connection between science and social, people talk about social media, this, that, and so on. So people who are communicating with each other, interacting, that's a data point. I mean, that's a sensor, so to speak, right? You go and type a text, or you place a picture, you tweet, or you do something, you're a sensor generating certain amount of data. All over the world, it's a virtual connection, right? You can have friends all over the world, right? So in order to understand the patterns and use that to do some actionable insight, to predict something and so on, requires something very, very similar in approach. So you may want to figure out what brands are connected with what. So I'll give you a very interesting example. Okay, so this is slide. This is an example. We were working with a company called Nicorette. Have you heard of that company? So they want to figure out, okay, we want to advertise our product. Who should they advertise to? Where those guys are, right? You can place it. Remember, you can place an ad on TV. You can place an ad on newspaper. You can in magazines, or you can tweet, or you can Google. By Google keyword searches, or you can those are the mechanisms, right? Yeah, NSA. Yeah. Okay, but the example that so people interact with different brands, right? So the top connection we found, people who should be targeted are people who are engaged with Santa Claus. Seriously. Have you seen, if you go to Facebook and you find a page for Santa Claus, it has millions of followers, right? It's a virtual brand, right? It's not Pepsi, it's a brand, right? It's a brand. Now, so why is it connected to Santa Claus? Number one. Number two, it shouldn't surprise you. How many of you have seen TV ads where you've never seen one ad in which you saw Santa Claus? Right? So it shouldn't be surprising, right? So can anybody guess why the biggest brand in social media to which people should be targeted for smoking cessation connected with? So, beautiful, right? So, lot of youngsters, not as young as me, but much younger, teenagers, others, are in social media, right? They are wishing to Santa Claus that their loved ones stop smoking, right? So that data, that insight sort of bubbles up and shows as a big target. Now for a company, these are the guys who are not smoking, right? If I'm a 9-year-old and I'm smoking, I'm not going to go to Santa Claus page and say, okay, sorry, right? I'm asking for somebody else. But if I post something on Facebook or in this thing, my dad or mom or cousin is likely to be influenced by that. So you go back and you target those people and use the network to reach out to those people. That's what actionable insight with big data is about, right? So that's, yeah. Okay, so I can probably, there's another very interesting example. One of the, you see Dentine users, number 3, connection, brand connection to Bing search engine. And number 5 is George Foreman cooking. No, see, it's a real example in this age group for which Microsoft spent millions of dollars in real world. So this is a real example of something I do on the side. Okay. When I showed this, they said, we don't believe your fancy algorithms must be doing some rubbish, right? So I said, but what's the problem? He said, how can George Foreman cooking be so highly connected with Bing? So I said, why didn't you ask that question about the first 2 connections? The first one is the Windows phone, the other one is Microsoft users. They said, but that's obvious. So I said, do you expect that to be highly connected to Bing? Yes. So I said, okay, if those 2 are correct, then why aren't these correct? Right? So then then you have to explain, right? The point I said was, have you designed your search engine to be used by only people who are interested in technology? Let's say you have household people, friends who are not interested in technology. Do they use a search engine? People use search engines for all of this. So I said, maybe people are stressed out using Bing, therefore they chew a lot of gum, so that's why Dentine users are showing up. I don't know, but so the point is that this is the way to sort of target. So how do you sort of, here is an example of taking this back to the science world. So I was talking about there are many, so you must have heard of DFT calculations in materials and so on. There are a huge number of materials that are calculated by simulation, massive amounts of data, but they are all siloed. So if you put them together, right, you don't need to go and do the simulations again. It's like Amazon putting your historic, customer A's data, customer B data, combining together to getting some insight. So you're putting scientist A's data, who's done 20 simulations, scientist B, scientist C, bringing it together to make a bigger knowledge base, right? And now you use the analytics and mining to do materials discovery. Okay, so this is a real example of discovery of materials just using the data from previous simulations of new materials, right? No new simulations of any property, right? Similarly, if you take the optimization problem, that can benefit significantly from data-driven approaches, right? So optimization problem, you have a lot of points and you're trying to find the best fit and so on. The way to, so the traditional methods, the problem in optimization is that there's something called curse of dimensionality. I'm sure you've heard, right? So when you have huge number of dimensions, none of those things work. But when you have huge number of dimensions, you can artificially create databases of points and then apply data-driven techniques. That's what people are trying to do. Okay. So here is an example of, this is again real example of based on some data Air Force stuff, that you can see that just by some simple data mining, the end results, optimal result, if you identify the right type of variables, can be obtained much faster than doing any simulations and so on. So just to end, this extreme computing and big data is not a single dimensional challenge, right? First of all, important thing to remember is big data requires extreme computing. The type of computing would differ, whether it's science, type of science, business, et cetera, et cetera. Google can afford to do millions of independent computers, et cetera, because the model is different, the end user model is different. Whereas in science, things are very much more correlated, right? So some of those things, models break out. But if you want to look at the challenges, there are many, many. And then just to end, I tried to create a chart. It's called a radar chart. And just to impress, I made it complex. But the whole point of this chart is that suppose I had to design a machine, okay? extreme computing system where I wanted to do both simulations, but I wanted to use that machine to consume a lot of data, whether it's generated by simulation, historical, coming from outside, and do a good job. What would I need, right? So today, if you look at a typical extreme scale computing, that's its signature. So I say, okay, performance of writing data. I mean, if you work in that field, you say, okay, everybody focuses on how fast can I get the data out of the machine, right? Whereas analytics requires very reading the data. Or communication tolerance, latency tolerance is much smaller. You can, in extreme computing, for obvious, I'm sure you guys did all this, all this stuff. But whereas I can tolerate a lot more latency in this. So if I had to sort of put it together, and if I have to call this machine big data extreme computing machine, then I would have to do something like this. So that's where, I mean, I know this was a sudden jump from, I skipped a bunch of slides going from there to here, but I just wanted to say that it's possible to bring those together and apply both models. Thank you.